So I'm not going to talk about static geometrical structure, but dynamical statistical ones. But before that, thanks to the organizers for the invitation. This work was done by a PhD student of mine, Tomer Goldfriend, who finished and is now in Paris, at École Normale, and together with Tom Witten. And here is the issue in a nutshell. Let's imagine that I have a very big container, and in this container there are particles. They can be of arbitrary shape. And there is a constant force forcing them in a certain direction, for example, gravity pushing them down, pulling them down. And let's make our life the simplest as possible. So let's assume that this whole system is at 0 Reynolds number. Everything is strongly overdamped. Let's assume that these objects are sufficiently big that they do not fluctuate, that they are not Brownian. And let's consider arbitrarily low concentrations. So that's a very simple, apparently very simple system. And so suppose I just sprinkle them randomly in the fluid, and then wait for a while for them to settle a bit and look at the structure. Now, I think a priori there is no reason to expect that there will be anything interesting or non-random in the structure of these objects, as they are very dilute. But the point of this talk is that actually the structure is very non-random. It is still disordered, but there are strong correlations, and these correlations cause the density fluctuations across this container to be strongly suppressed, so that if you look from above at the XY plane, you're going to see a suspension that is as uniform as a crystal. Okay, so to sink in. If you wait for a while for the steady state, this is going to be as uniform as a crystal. Disordered, but very uniform. They don't have to be. I'll come back to it in the. Yes, it's a very general phenomenon. So what I'm going to talk about, actually, the real work is about density fluctuations of forced irregular objects. So they're asymmetric. But most or all earlier works on sedimentation were about symmetrical, spherical, or spheroidal objects. So I will say a few words about that before. And before that, I'm going to make some electrostatic analogy, because electrostatics is something that we are supposed to be more relaxed with. But I will begin with a very brief introduction about what hyperuniformity is. It's a relatively new buzzword, if you like. People who are interested in this term, hyperuniformity, there are two reviews, an older one and a very new one. It's like 100 pages long, so I warn you. Hyperuniformity, so what is it all about? Suppose I have a collection of particles, spheres, points, and it is distributed in space. And suppose I take a window of radius r, and I move this window throughout the material. And I ask, what are the fluctuations in the number of particles inside this window? Okay, so this is delta n squared averaged. If this is a fluid, then the central limit theorem tells us that this fluctuation or this variance in the particle number is going to be extensive. So it's going to be the radius of this window to the power of the dimensionality, r to the power of d. So this is one extreme, and the other extreme, suppose these particles are arranged in a perfect array, in a crystal. Then, of course, it's very uniform, but still there are fluctuations that come from the surface, whether one particle was included or was excluded. So in that case, the variance is subextensive, and it goes like r to the power of d minus 1. So this is very uniform. This is very disordered. So hyperuniformity refers to cases where this power, nu, is in between d minus 1 and d. Any system that exhibits such suppressed fluctuation is called hyperuniform. This is one characterization, and there is another characterization that is almost equivalent, and that is, it's more useful, so I'm going to introduce it. Instead of talking about a window and a number fluctuation, we talk about the structure factor. That is, you take the 2-point density correlation function and Fourier transform it and take thermal average, any average, and that is called the structure factor. In such a case of a disordered material like a fluid, the structure factor decays to a constant as Q goes to 0. As I go to larger and larger length scales, I saturate to a constant. And in hyperuniform systems, it goes to 0 as Q goes to 0. So there is Q to some power alpha, such that when I go to larger and larger scales, the density fluctuations are suppressed, such that the structure factor vanishes. This phenomenon has been observed in several experimental systems, not so much actually, so it's still unclear how important it is in practice, but it has been observed. One system is a suspension that is put in between surfaces and sheared periodically. Under certain circumstances, it becomes hyperuniform. Another example, which is very important, if it turns out to be correct, still under controversy, is if you take a random close-packed arrangement of spheres, of colloids, this is an experiment by Eric Wicks and co-workers, then you are going to get a hyperuniform structure. So it's not what they claim, it's not a frozen liquid. It's a new kind of structure which is hyperuniform. Whether this vanishes or not, it seems that it does, but it's still under debate. It's hard to prove that as Q goes to 0, a structure factor goes to 0. So these are two examples. There are also schematic models that reproduce this effect, yes? No, here this is some alpha, which is related to nu. It is mapped onto nu, and this, yeah. So the only thing you need in principle is that it should be non-zero. Okay, the value they did measure it. I don't remember the number. The point is whether it vanishes or not. The claim is that it vanishes, and there are all kinds of artifacts to overcome experimentally. But yeah, if this is true, then it is important. If any random close packing is hyperuniform, it's an important phenomenon. But it's unclear yet. No, sorry. So okay, so I was not clear enough. You can talk about all kinds of fluctuations, and I'm talking about all of them in one basket. Here, we are not talking about thermal fluctuation, but just density fluctuation in the frozen structure. You take this window, and you count how many numbers fall in this window. So this is a static system, yes. Both of these examples actually are static. So it depends, when you do the average, what kind of average are we talking about? It can be an ensemble average or a spatial average if the sample is static. So there are some schematic models that were very thoroughly studied, mainly by Daniel Hexner and Dov Levine, and Chaikin also. Here you can see a random organization and how the density map looks like for this structure. And these are two schematic models. I will not get into the details. If you're interested, I can tell you later on, that produce much more uniform density fields. And here is a crystal, and it's very uniform. Okay. So this is just to say that these systems are not a matter of imagination. They have been observed experimentally and numerically for sure. Now for an example, I'm going to show an example that is actually known. It is known to be hyperuniform. So I'm just telling you this example in order to have an analogy to the sedimentation problem that is slightly more complicated. So we are talking about electrolytes now. So an electrolyte is composed of positive and negative ions in water. And instead of talking about the structure factor of all of the ions, let's talk about the structure factor of the difference in density of the two ions, which is the structure factor of the charge density. So I will call it S rho. So this is just, again, the Fourier transform of the 2 points correlation in the charge density. And here the average is thermal average. It is a well-known result from the 60s that S of Q of the charge density decays to 0 as Q goes to 0, it decays quadratically. And soon I'm going to tell you why. And if you, in the language of hyperuniformity, it means that if I take a window of size R and I ask what is the fluctuation in the total charge in such a blob, then it scales like the surface of the blob and not like the volume of the blob. So again, there is this funny conclusion that if you take an electrolyte, which is a very disordered and a dilute system, and you ask how does charge fluctuations look like, they are as suppressed on the large scale. They are as suppressed as in an ionic crystal, which is again strange but true. One way to look at it is to understand it. Yes. The thickness. Yeah. The plasma frequency. Uh-huh. Yes, of course, but I'm not sure. The claims that I'm making have nothing to do about dynamics or excitations, just about the static structure. But you say it's equivalent in some way. Yes, sure. Yes. Yes, incompressible. You're right, yes. So this whole weird behavior comes from conservation law, of course. In this case, the conservation law of charge, because we know that conservation of charge tells us there is a Poisson equation. So if divergence of the electric field is proportional to the charge density, which means that if I take square and take the average, etc., I'm going to have a structure factor of charge density that scales like q squared times the fluctuation in the electric field. So now you face two options. One is if the fluctuation in the if this structure factor goes to a constant as q equals 0, it means that the fluctuation in E goes to infinity, because it will go like constant divided by q squared, which is not something very pleasant, because E squared is an energy density. So the only other option is that the S rho itself will vanish, and then E squared can be finite. So that is the physics behind this hyperuniformity. Now we can go further and say, okay, that means that there is some distance, let's call it lambda, at which the behavior will cross over from normal fluctuations that are extensive, that go like r cubed, to these suppressed fluctuations that go like r squared. So let's call this distance lambda, and let's try to extract the basic physics from which it comes. So what will cause this random distribution here crossing over to hyperuniformity is thermal noise. So let's take the electrostatic energy that is associated with such a blob of charge Q, and demand that at a blob of size lambda, this electrostatic energy should equal to AT. Then you get this lambda, and this lambda is nothing else but the Debye-Huckel screening length, good old screening length. Which means that one can think about this screening length as a hyperuniformity length. That beyond that distance, charge density fluctuations are strongly suppressed, and the material is basically as neutral as a crystal. Okay, so this is just to have some language to talk about a system that we know a lot about, which is electrolytes. Now I'm going to use very similar arguments to talk about sedimentation. Now sedimentation is an old problem, but it is considered unsolved, to the extent that there are two reviews here which are completely contradictory. So there is this approach by people from statistical mechanics, an approach by people from hydrodynamics, and the basic assumptions are completely different. So first of all, I would like to tell you that it's a complicated system. Again, you can see here results of two famous experiments. Phi is a volume fraction. Please note how small the volume fraction is. The particles are big enough so that they are non-Brownian. And therefore, all this chaotic behavior and highly dynamic behavior that you see here comes not from thermal fluctuation. It comes from the chaotic dynamics of the system itself. So these are not just particles that settle very quietly down. They are very large-scale fluctuations. And this comes about because these particles are strongly and they are strongly coupled and over very large distances hydrodynamically. If you have one particle that is pushed by gravity down, then there is flow created by that forcing, and this flow drags along the other particle. And this coupling is long range, and it is described by something called the Sin tensor. It decays only like 1/r. So this makes the whole system mutually coupled, and that's what leads to this very complex dynamics, which is still not solved. Now the point is that what we realize that if we take the particles to be arbitrarily shaped and not spheres, actually, of course, the problem is much more complicated, but in this sense, it is solvable. I mean, we understand what's going on. They are so strongly coupled that in the mid-80s, there was a prediction, famous prediction by Kaflish and Luke, that if you look at the variation in the velocity of each and every particle in a sediment, in a sedimentic suspension, this velocity fluctuation should diverge with system size. Why is that? Here is a very simple argument. Let's assume, let's look at a subregion of size r within such a sedimentic suspension, and let's assume that the density fluctuations are normal. Therefore, the variance in particle number is going to be extensive. And suppose, because of this fluctuation, this area is slightly heavier. If it's slightly heavier, it has some fluctuation in the force acting on it, which is proportional to the fluctuation in particle number, which means that the fluctuation in the gravitational force on this region goes like r to the 3/2, just simple algebra. This is going to be resisted by additional friction, which goes like Stokes. So it's a viscosity eta times the size of this region times the fluctuation in velocity. Because again, if it's heavier, it's going to sink slightly faster. And delta U is this difference in the settling velocity. And then you can just isolate delta U, and you get that it's proportional to the square root of the window size. So as I go to larger and larger windows, this velocity fluctuation diverges. But you see, I emphasize this. This whole argument assumes that the density fluctuations are normal. So probably it's not true. So here is a result from another experiment by Guazelier and co-workers about a decade ago. So you can see here two settling suspensions. These arrows are just the motions of the particles. This is in the beginning of the experiment, and you can see huge fluctuations that span the whole container, but this is after some time. And you can see that everything has been suppressed and relaxed, both velocity and probably also density. Again, you can understand it based on conservation, in this case conservation of momentum, because if I have this suspension with concentration C, then I have a density of force monopoles. Each particle has an mg acting on it, so it's it's like a charge monopole, but here it's a force monopole. It's slightly more complicated because it's tensorial, vectorial, but apart from that, it's the same. So again, I have an equation of conservation, in this case, conservation of momentum. And if you do the same trick, you find that unless you want your fluctuation in the stress to diverge, you need this S of Q to vanish as Q goes to 0, and it should vanish like Q squared. Again, a very similar argument. Here you can see the fluctuation in the particle number as a function of the size of your region, or the mean number of particles in the region. And you can see that in the beginning of the experiment, it's a different experiment. Beginning of the experiment, the fluctuations are normal because they are now normalized by the mean particle number, so it's a constant. But then as time goes by, the fluctuation becomes more and more suppressed. So it's actually, it is verified experimentally. Not accurately, but qualitatively. Okay, so let's do the same trick, but now assume that the fluctuations are not normal in the density. If you do the same calculation, which is, again, you can do it on the back of an envelope, you find that if your hyperuniformity is maximum, in the sense that is as uniform as a crystal, fluctuation goes like the surface of your sub-region, then you are okay. I mean, the fluctuation in velocity is finite, and you have no Kaflish-Luke problem. And so That's a way for the system to avoid very large stresses by suppressing the fluctuation in density. Yeah, excellent. So it's here. Assuming that a certain blob just goes as a coherent object is true only if you have strong hydrodynamic interactions. The fact that these objects here interact like 1 over r among themselves is what gives you the justification to look at this blob as a sphere and apply the Stokes formula. In polymer physics, it's called the ZIM model. Okay, and if you do it rigorously, of course, that's what you get. I mean, that's not a real calculation, just the basic physics. Otherwise, you would have friction applied to each and every sphere, which is a completely different calculation. Okay, it will be the number of particles here times 6 pi eta small radius. It will go like r to the power of d. No, but still, each one of them will have a velocity fluctuation delta u. Again, we can ask, okay, what is the distance at which there will be a crossover from normal to suppressed fluctuations? And again, I don't have time, but again, it's a very simple argument. And you get a distance, which is a screening length, a hydrodynamic screening length in this case, which scales with the volume fraction, like the concentration to the -3rd. So all this is very nice. So there are density suppression of density fluctuations, which cuts off the fluctuation in the velocity, but I didn't tell you why. I mean, what is the mechanism? Okay. It's just if I have this, I will have that. But why should I have suppression of fluctuations? And actually, the mechanism is not clear. Again, there is a controversy. So there are all kinds of mechanisms that have been suggested, and I'm going to focus on this one, which is coming from fluctuating hydrodynamics. It's the paper, and Robin is one of the authors here. So I'm going to present this approach very briefly. It's a fluctuating hydrodynamics. So you have an advection diffusion equation. C is the fluctuation in density. F are some random fluxes, and this is an advective term. U is the fluctuation in velocity. So this is a diffusion equation with noise. The point is that once I know C, the fluctuation in concentration, I know immediately the fluctuation in the fluid velocity through this oscillometer. And for the noise, we can assume the simplest assumptions of Gaussian white noise, local. And here is an important point. I'm talking about the simplest case, which was treated by Alex Levin and co-workers. I take point-like particles, then the velocity of the objects, u, is equal to the velocity of the fluid around them, if they are point-like. And also, if they are spheres, then the velocity is not equal, but still the divergence of u is equal to the divergence, is proportional to the divergence of v, and it is 0 if the fluid around is incompressible. Now, in this case, if you look at this linear term, there is a linear contribution which goes like c naught times the divergence of u, but it is 0 here. And then I'm left only with a nonlinear term, and this problem is complicated. It's a nonlinear fluctuating hydrodynamics problem. Now, what is going to happen is that if the particles are not spheres, but are going to be asymmetric, then this will not be the case, and I will have a linear problem. So although the particles will be of arbitrary shape, which is apparently a more complicated problem, I will have linear screening, which we can easily understand. Physically, what it means, this mathematics, is that if I put spheres or spheroids in some kind of complicated flow, they don't have to flow with the same velocity of the fluid around them, but they will follow the flow lines. They don't have any freedom in the direction. That's what it means, the vanishing of the divergence. This is not going to be true for asymmetric objects. And this theory does give you hyperuniformity. If you, Alex Levin and co-workers, they calculated the structure factor, and it's as q goes to 0, it goes like q squared. So indeed, the suspension is highly uniform. And they get the same screening length that I got with this hand-waving argument. But you don't need more than that. You don't need more than that. I don't know. So there are very heavy assumptions behind this model. One is that this white noise, and B is that there is this diffusion with the diffusion coefficient that I don't know where it comes from. Because there is no thermal motion here. It's just some chaotic. Who says that I can represent the noise in the system by some simple diffusion coefficient, for example? No fluctuation dissipation. So again, heavy assumptions that are unclear whether they are right or not. Okay, now to the work itself in the last 2 or 3 minutes. It has to do with objects that are asymmetric, and Tom Whitten and his group have been involved in studying such objects for some time. Here's a result of an experiment by Robert Deegan. If I take an object that is asymmetric, it has an eigendirection. It chooses some eigendirection and then falls along this direction and rotates around it. So it has a chiral response along a certain eigendirection. Here it's again. If you can look at it, it chooses some direction and then continues to rotate around that direction. The point is that it has a direction. This is a reproduction, a theoretical or numerical reproduction of this phenomenon. I don't have time. The response of such a single object was very well characterized, so I will not go through this mathematics, but the point of this slide is that this special object that you saw in the previous movie is not special, it's a general rule. Most objects will behave like that. If you just like space of all objects, most of the objects in this space will be self-aligning. They will choose a direction and rotate around it. So it's not some kind of an esoteric thing. The sphere is esoteric. If we repeat the same model with all its problems and just assume that the particles are asymmetric, now we also characterize the response of such an object to non-uniform shear flow around it, and this response can be characterized by a third-rank tensor, which we call phi. To the current argument, what it means is that if I take the divergence of u, it's not 0. That's the only point that is important here. And that's because of the asymmetry of the response of the object to the flow around it. Again, physically, it means, unlike spheres that just follow the flow lines, such objects have some direction along which they want to fall. Okay? And that makes them not follow the flow around them, because they have some kind of restoring force that tries to return them to the preferred direction. And therefore, if I have such a region, I can have a net flux inside or outside of that region. Okay? If this region is slightly heavier, I can have a mechanism that pushes particles outside and regularizes this density fluctuation. That's the idea. So just repeating the same model. So what it gives you a linear term here, right? Because now I have C naught times divergence of u, and this is a linear theory, and it's really trivial to solve. So one gets a new relaxation rate from this linear term and a screening length, again, a new screening length that comes from competition from this random diffusion, whatever it comes from, and these hydrodynamic forces. It's not clear that in such a system you will have a very simple linear diffusive term. Yes, sure. No. Sure. These two assumptions are interrelated, but again, both of them have not been checked experimentally at all for some reason. Sure. It could have been checked experimentally, but it was not. So it's still open. And the whole argument relies on that, including our argument. So it is a problem. So we can calculate the structure factor, which is, again, hyperuniform. It goes to 0 as Q goes to 0. It is anisotropic also, so there is no hyperuniformity along the Z direction. The hyperuniformity is only across the XY direction. Except for the fact of when Q is actually parallel to Z, in any other case, if I go to Q equals 0, my structure factor is going to vanish. So I briefly described the regularizing mechanism here, coming from the fact that these objects do not have to follow the flow lines. And therefore, if I have a heavier area here, they can flow outside and regularize it. But who says they regularize? They can also flow in and deregularize it. And that is indeed possible. There is no law against it. And we found examples where this screening term becomes, okay, the screening length become imaginary, which means that we have an instability. It happens where, for example, if you take spheroids whose center of mass is shifted from the geometrical center, you get a self-aligning object. And if it's prolate, then the mechanism is stabilizing and we get a hyperuniform expansion. If it's oblate, then it's the opposite. And you have an instability. Again, there's a strong prediction that for experiments that was not observed. This I can explain very intuitively, but I think I don't have time, right? Okay. Well, the point is that suppose I have here an area that is heavier, okay? So this one sinks a bit faster than on the right, okay? So it's quite clear that if I have such an object, it will be tilted away from the heavier region. But if it's an oblate, it's the opposite direction. So that's all there is in it. And yeah, that's it.